Yeah, go ahead. Yeah, you can look on that. That's the kind of the good thing about the article. I made sure that was in there just so we can you start seeing what we're starting to build towards for this atomic model, right? There you go.
This may be incorrect.
Try it. Have full confidence.
These are negatives. That's what he thought, I think.
Kind of, yeah. So you're right in the sense, but I think it's more like.
Oh, that's supposed to be a nucleus.
Yeah, that's supposed to be a nucleus. Yeah, there you go. So this is a really dense center, and then you have, this looks like a donut, but, and it's hard to draw it like the rest of what it would like actually look like, you know? But yeah, you're exactly right. A dense nucleus, a cloud around it, a bunch of electrons everywhere in the cloud, right? Does that make sense for everybody? Yeah, it'd be hard to kind of draw that. Like you have to like, I think in the model that it gives you, it's like a loop here, and you're gonna like do that, and now it just looks weird.
Because it is weird.
Yeah, it absolutely is weird. But that's kind of the initial model that Rutherford came up with. So we're still missing a part of this, right? Because we've got protons, we've got electrons. What are we missing? So we're going to develop that with the next few articles. But first, we're going to go through and just kind of catch up on these notes here, these fill-in notes, just to make our lives a little bit easier, so that you all have the information kind of organized. So that way, when it comes test time, it'll be easier to kind of look through and kind of remember. Oh yeah, that's right. We talked about like Dalton's theory and Rutherford's experiment and whatnot. So I'm gonna go ahead and put these on there. Are we gonna fill this in together? So let's just go through the blanks here. So let's see here. Top blank. Blank, the smallest particle of an element that retains the properties of the element. What do you think it is? Atom, right? Everybody kind of said that at once, right? So I think we all understand that part, so good job. So now we're going to go to John Dalton's theories. So for John Dalton, this one already covers one, and this is kind of like what we kind of talked about in class Tuesday. Y'all weren't here for that, but when we got introduced to that. So he said all elements are composed of tiny indivisible particles called atoms. So this was kind of the first difference between this and the present theory. The second difference that that this theory has that the present theory does not have comes right here. So he said that atoms of the same element are what?
Unique.
He didn't say unique. He said something else.
They're like the same properties.
He said identical. You're right because of the present day theory, because that's correct. They have the same, or they're unique. But in this one, he put identical. So there's a big difference when we go into present day theory between when he said all the atoms of the same element are identical, and all the atoms have of the same element have unique properties to themselves. There's a big difference between the two. We'll find out. So number 3, atoms of different elements can combine with one another in small what?
Definite whole
Particles?
You said whole number ratios, definite ratio. Seems like y'all kind of are on the same page here. Anything else? Any other thoughts on that? No? Yeah, so yeah, whole number ratio. So this is kind of labeled as the law of definite composition, and again, that kind of swapped to the 4th one in present day theory. Don't really know why, but I think it's just kind of just ordering it better because they want law of conservation math first. So, and of course, number 4, I feel like we've harped on this a few times already, but chemical reactions determine atoms are separated, joins rearranged, however atoms of one element are not changed into atoms of another element in ordinary chemical reactions. Law of conservation of mass. I know that's probably one that you hear a lot. You probably heard it like back in the day, and I think that's one that's really popular to listen to know, but we're just redefining it here essentially. So, present day theory. A, element is composed of extremely small particles called what? Atoms, right. Atoms of a particular element have a unique set of chemical properties which distinguishes them from atoms of all other elements. So, the reason we say this, and I don't think you got the video on Tuesday, so I'll kind of talk about this now. We'll talk about this later, but I'll just introduce the idea here. So the reason that is atoms, there are these things called isotopes. We'll get to these in like a day or two, but essentially not all atoms are identical because every atom can have a different isotope. Like for example, you hear about carbon-14 dating, right? Have you ever heard that term before? So that's an isotope of carbon, right? So carbon normally only has, I think if I remember correctly, it has 6 protons, 6 neutrons only, carbon-12, right? But carbon-14 refers to it having 2 extra neutrons, and that isotope tends to be extremely unstable, and so it has a half-life. And the half-life describes how fast a particle deteriorates. So that's kind of what they use for that, and so that's why we say each element has a unique set of chemical properties rather than every single element of the same, or every single atom of the same element are identical. Because carbon-12, carbon-14 are going to have unique sets of properties based on them being carbon, but they're not the same. They're different stabilities. So that's why we mentioned that in present-day theory. We'll talk about isotopes a little bit later, but I just wanted to mention that now just so that y'all aren't confused on that.
I remember that in 8th grade.
You remember that in 8th grade?
Yes.
Yeah, I feel like a lot of you have at least heard about carbon-14 dating and stuff, so I was just,
And we're gonna discuss radioactivity in the
Yeah.
next unit in great depth.
yeah. So, moving on. Of course, in ordinary chemical reactions, atoms do or don't appear, disappear, or change the atoms of the element.
No, I don't.
Don't, right? Law of conservation of mass again. Atoms are not created, destroyed, or changed in the periods of a reaction. All right? And in a particular compound, the atoms combine. We kind of already said this. They combine in what?
Whole number.
Yeah, fixed whole number ratio. I mean, it's essentially whole numbers. We can talk about when we get into bowls. We'll talk about that. But like, you can't have half an atom. Like that just doesn't exist. Again, I think I don't know if I talked about it with you, but like you talk about fiction. You have half an atom. What happens? You split it out into half. Right?
Fission.
Yeah. So you can't just have an atom in a reaction here. Okay. So here's some kind of examples of that: the water, carbon dioxide, sugar, and glucose. Notice how there's no halves in any of these. These are all whole numbers when we're talking about these. And then, what are formed when 2 or more elements chemically combine with each other?
Compound.
Compounds, right? You can also use like molecules. Molecules is also another word we use for that. Because you've got atoms and you've got molecules, and so we can kind of refer to them as either. All right. So, but this is when we get into our talks with the articles. So, let's kind of put what we put in the articles into note form so that we can have them for the test, right? So, electron discovered by J.J. Thomson, 1897, using cathode ray tubes. It has a what charge?
Negative.
Negative charge, right? Located outside the nucleus in energy levels. The more energy the electron has, the what is this from the nucleus? Do we have any idea on this one?
Farther.
Closer or farther? What do we think?
I think it's farther.
You think it's farther?
Because it requires more energy to get, like, move around the center. Because there's, like, more circumference.
Yeah, because So yeah, the more electrons you have, generally the farther it's going to be out from the nucleus. So that one I don't think the article specifically talked about, but that was good reasoning on that, Cooper. So it has the mass of 1. Can I say this fraction? I forgot. 1/1837th that of a proton. Therefore, it is what in the overall mass of the atom? Smaller, right? But like, do we care about 1/1837th of a fraction, right? Like, if you had 1/1837th of a cookie, would you eat it?
Yes.
You know, okay, true, but would it be satisfying?
No.
Yeah, no, it wouldn't be satisfying, right? It doesn't really count. So yeah, Robert A. Michelin discovered the actual electrical charge. We'll talk about him in like the near future, because he discovered the actual electrical charge of the electron using his oil drum experiment here. So let's go to our nucleus here.
So, if you pluck a hair, do you think do you say you lost weight? Does your hair have mass? Does your hair weigh something? It's just so small in comparison with your overall weight
Mhm.
that we just don't figure it in. That's the way the electron is.
Yeah. All right. So let's see. This one is. I don't think the article covered part A. It kind of covers it. So the nucleus contains what, along with hundreds of other subatomic particles called nucleons. So if we have the nucleus, we have, what do we know that's inside the nucleus? Protons, right? So we know there's protons in here. Do the notes contain protons and neutrons on this one, or is it just protons?
Yes, protons and neutrons.
Okay, gotcha. So this one they talk about protons and neutrons on this one. So remember, protons and neutrons on here. Okay? So let's talk about the nucleus. So it was discovered first by Ernest Rutherford with his gold foil experiment, which gave 3 conclusions about the nucleus of an atom. So all atoms contain a what nucleus?
Positive.
Positive nucleus. So specifically, the term we're going to use positively charged nucleus. But you're right, it is a positive nucleus, but again, we're going to say positively charged, just to keep the terms in mind, right? All right? The nucleus is very tiny, it contains relatively blank of atom, therefore it's very dense. So, do we have an idea of how to fill this one in? Yes or no? No clue? So, remember how electrons